Basic agenda for today. We're going to cover quick introduction, important disclaimers, talk a little bit about traffic engineering prior to MPLS, basics of traffic engineering tunnels, distributing the appropriate information amongst your routers, path calculation and setup, forwarding traffic down your tunnels, and a little bit more on diagnostics. So important disclaimer here. I have not been exposed to Juniper operating system. I've never touched a Juniper. I've worked with Riverstone but didn't do any MPLS work on those. I am a Cisco only shop. It just happens to be what I'm doing. Apologies that I don't have any Junos configuration examples. If this seems useful to you and you have a buddy who can help you out, I'd be happy to act as a third party in that angle to help out there. Please ask questions as they come up. This builds on a lot of topics. There are several checkpoints along the way to help us make sure we're on track and we're all kind of tuned in. But please pause me at any point, go up to the microphone, and we'll talk about it. If we end up early, we'll switch laptops and poke a little bit into my production network. Usually every day around this time, traffic engineering is kicking in one spot or another. So, and obviously, there's no fancy corporate logos on here. This is not a vendor-driven tutorial. This is from an operator perspective. I use this stuff. It becomes very valuable to my network. And it's geared as much as I can to those of you who are network operators. So diving right into it, traffic engineering prior to MPLS. If you've got IGP of some form, let's say it's ISIS where default metric is 10 in all cases, commonly known as the fish problem. If you get a little bit creative, this will look like a fish to you. And if we throw some traffic over it, we'll find that all of our traffic coming in on A or B, headed out G, wants to go through C and D, and never through C, E, and F. There are ways to tweak that. We can go in and muddle around with our IGP metrics and adjust them, but you've really got to have an incredible understanding of your network, soup to nuts. Know what tweaking a metric by 1 here or 5 there will do to all of your traffic. And if you end up with some mismatched metrics, you can end up with some routing loops and other sort of forwarding funnies. So we can go through and change the metrics C to D and D to G, and we'll find that, theoretically, based on our load sharing hash, that traffic's going to spread over the 2 paths available and be able to use more of what our network offers. Obviously, in this scenario, we don't have any redundancy left over, but we're able to handle traffic that otherwise would be unable to use the links through E and F. So our fundamentals moving into traffic engineering on MPLS, we all know that packets are forwarded based on our FIB or our LFIB if you're already running MPLS forwarding, and it's all built on your RIB. The RIB obviously is driven on next hop information. What interface do I egress on? What's the next hop MAC value or whatever? And again, here we're dealing with routing production network traffic, so we need an exit interface. And because we want to travel it across our network over a deterministic path, we bring in the new concept of the traffic engineering tunnel. So fundamentally, our traffic engineering tunnel is a unidirectional logical link from one router to another router, unlike a GRE tunnel, which is normally bidirectional back and forth. Once the tunnel is properly configured, a label is assigned for that tunnel hop by hop through the network, so we end up with a label switched path. The path through the network will be deterministic, meaning all the packets traveling over this tunnel will follow the same hop by hop path, at least until various reoptimizations or adjustments that we will talk about through the tutorial. And that deterministic path may not be your IGP shortest path. So it allows us to utilize other links in your network that aren't the best route from point A to point B. So once traffic is routed on the tunnel, and we will find that that takes a lot of steps, the traffic then flows through the tunnel based on the path assigned to that tunnel. Return traffic going the opposite direction could be placed onto a tunnel that travels in the opposite direction as well, or you could simply allow it to be routed by the IGP. There will be some scenarios in our caveats at the end that you really want tunnels going in both directions, but if you're doing plain vanilla packet forwarding, not that necessary. So, a couple of key terms for traffic engineering. Head end is where you configure your traffic engineering tunnel. Because the TE tunnel is unidirectional, there's no need for a traffic engineering configuration on the opposite end. So the only place that we do any real TE configuration is, again, on that head end. In this case, router A. The tunnel tail is the destination address of the tunnel, as pictured here, router D. And midpoint routers along the path are anything that's in the middle. There may or may not be any midpoint routers. There are scenarios where you'll do a tunnel from one router to the next router because you may end up punting that traffic through a non-best route because you simply have congestion over that one link. But in this case, the midpoint routers are B and C. So diving into some basic traffic engineering configuration. On each router where you want to do TE, you need MPLS traffic engineering tunnels. Enables the code that then follows thereon into your IGP. And in the case of MPLS traffic engineering, the only options are OSPF and ISIS. If you're running EIGRP, there are no mechanisms inside that IGP to carry the various parameters in LSAs that are necessary to knowing where can I put this tunnel or that tunnel so that we end up on a link that has bandwidth available. And then on the physical interfaces across your WAN or network, whatever boundaries you anticipate doing traffic engineering, that physical interface obviously needs MPLS IP so it can forward labeled packets. And it's also going to need MPLS traffic engineering tunnels. That signals back to the IGP to share the traffic engineering information, how much bandwidth is available at various priority levels with the other traffic engineering nodes where you've enabled all these commands. And it ends up kind of being a big synergy of routers with an information of bandwidth availability throughout your network. Then when it's time to start bringing up traffic engineering tunnels, we start creating interfaces that are simply tunnel X. You'll have to work on your own numbering scheme. Feel free to ping me afterward for some guidance. I'm one example, and I'm sure there's others who we could contact to get other ideas. In order to be able to forward IP packets, we have to have an IP address on there. Because these are unidirectional, burning up /30s on your TE tunnels would be rather wasteful and inefficient. So we can just borrow the loopback address and be able to forward traffic. Tunnel mode has to be changed from GRE to MPLS traffic engineering. And like any other tunnel, we need a destination. And it would be the defined address, ideally your loopback 0, of the tunnel tail. And then we need to find a way through the network. And this covers all of our dynamic path selection or explicit path selection, which we'll get to. But for lack of a better example, if you just want to bring up a traffic engineering tunnel, assigning tunnel MPLS traffic engineering path option, pick a number, and say dynamic, the tunnel will find a path, essentially the best path through your network, that has an appropriate amount of bandwidth. In this case, we haven't defined any bandwidth parameters on the tunnel, so it'll be a 0 bandwidth tunnel and it'll find the best path. So we're at checkpoint 1. Looking back over what we've zipped through, tunnels go from a head end to a tail end, possibly through midpoint routers, over a deterministic path that stays the same until various reoptimization events. We've covered the commands that go on a router at a global level, on physical interfaces, and on our TE head ends, what commands are necessary for each traffic engineering tunnel. So now we're going to dive into traffic engineering and its relationship with bandwidth. And again, if you've got questions, please walk up to the microphone, and because this builds on a lot of stuff, I'd like to get those covered nice and early. Traffic engineering and bandwidth. Your physical interfaces, LAN links, WAN links, MAN links, whatever you've got flowing through your network, can be told how much bandwidth can be reserved, meaning used by traffic engineering. IP RSVP bandwidth XX. The numbers end up being put in there twice. It really defines microflows, which aren't really relevant in this scenario, so just repeat the number. Our traffic engineering tunnels, as configured on the various head ends of the network, can be configured with how much bandwidth is needed on a per tunnel basis with tunnel MPLS traffic bandwidth Y. Our tunnels will reserve through RSVP Y amount of bandwidth on their outbound interfaces, and in doing so they will find a path across the network over various best or almost best interfaces such that the interfaces used will have more bandwidth available for reservation than the tunnels are requesting, so that we, at least in the concept, don't oversubscribe our interfaces. There are lots of design models that don't pay direct bit-for-bit attention to our bandwidth consumption. That's certainly an option that I've got built into a separate design tutorial that'll come at a future NANOG. There are other ways, perhaps, when you're setting the bandwidth available on an interface to allow yourself a 10%, 50%, whatever cushion you want, so that various microbursts, flash crowd events, what have you, have room to operate. But this is our fundamental concept of traffic engineering and its relationship with bandwidth. So obviously you can manually or automatically hop into your router and adjust those tunnel bandwidth values as time goes on, hourly, daily, monthly, whatever suits your network, to match the changes in your traffic. And if those tunnels have a path option that's dynamically assigned, the tunnels will dynamically find a path, hop by hop through your network, that has sufficient bandwidth, or, this is the important point here, go down, which means they will fall out of your rib, they'll fall out of your fib, and those particular tunnels are no longer used for traffic engineering. And if nothing else, it gives you indication in your logging systems that, oops, I've oversubscribed whatever values I've programmed into my network, and it's time to run around and take a look at that. We'll also look at some various diagnostic commands to be able to assess how we're doing as far as bandwidth being reserved actively on the network based on the physical configurations we've loaded in there. And then comes some of the traffic engineering magic, and this happens to be something I rely on, perhaps even abuse. Our traffic engineering tunnels can be configured to watch their actual traffic, as in inside the router says show interface blah pipe include rate every 5 minutes. And of course, because these are unidirectional logical links, there's only going to be outbound bandwidth. There will never be inbound packets on a TE tunnel. And they'll do this at periodic intervals. So now we begin to have dynamic reservations that match the live network. So if you have traffic bursts, it won't be instantaneous. In my case, I run a very aggressive auto bandwidth scheme so that within 15 minutes, my network rearranges TE tunnels so that we try not to oversubscribe links. Obviously, you can drop a lot of packets in 15 minutes, but for where we are, it keeps things under control in a reasonable time scale and allows us to breathe easier when things happen, and perhaps we can focus on the next most important thing. Perhaps it's identifying a DDoS attack and source and destination and start looking up null routes. Perhaps it's simply a particular traffic shift due to an outage event or a traffic change, and start looking at retuning BGP and allow the WAN, in our case, to readjust itself without us really having to worry about it. So bandwidth is reserved using RSVP in this algorithm. However, keep in mind this is not particularly a QoS mechanism. The traffic that you reserve for MPLS traffic engineering is only a number in a control plane. It's not actually going to force the router to prioritize that much bandwidth out your interfaces for MPLS traffic engineering. There's lots of other QoS things you can do with MPLS. I'm not going to cover them. I'm not using that in my production network. There are some other experts we can bring in if that sounds appropriate for a future NANOG. So to actually implement this, tunnel MPLS traffic engineering auto BW frequency Y. Each auto bandwidth tunnel will do a show interface to capture its rate every 5 minutes. This number is globally adjustable but the capture ratio is global, not per interface. Each auto bandwidth tunnel will update the actual configuration in your router that shows tunnel MPLS traffic bandwidth X every Y seconds, whatever you've set it to. I believe the Cisco default is 1 day, so it's a real slow generic adjustment there. In my case, Y is 900 seconds, 15 minutes, so 3 captures. Over the span of Y seconds, you'll have however many 300-second intervals are in there. The highest single interval is used as the reference when updating the tunnel bandwidth every Y seconds. So if you've got one 5-minute period somewhere in the course of your day or your hour or whatever that was hot, that's going to get captured and stored locally. And as a bit of a tangent, you may want to tweak the interface load interval because it's an exponentially decaying function. By default, that's a 5-minute supposed average, but because of the decay, you're probably more looking at 7.5 minutes of relevant data factoring in. I feel comfortable with 5 minutes, but some folks may want a more accurate snapshot of instantaneous traffic. And as I pointed out in the slide, this auto bandwidth is changing your configuration. If you do a show run and you wait 15 minutes or you wait a day and you do another show run, you'll see the numbers have changed. It's really in there. If you do a copy run start, those numbers are really in your startup configuration. So those of you who capture your router configs every day may want to try and work on an exclusion mechanism, because our core routers every day fill up our email box with configuration changes that are really just bandwidth adjustments that we're not really paying attention to. So those of you who are hopefully automating your configuration, or at least your tracking, this is a key point operationally. Okay, another pausing point. We've covered traffic engineering tunnel basics. We've covered router configuration basics. Now we're going to we've also covered general concepts about traffic engineering and bandwidth. Now we're going to plow into how do we find a path through our network. And this is essentially disjointed from our IGP. So now we get to path calculation and setup. And this revolves around a constrained version of SPF. We're going to find the shortest path through the network that meets certain considerations. In our case, the shortest path that has X bandwidth available for reservation. Technically, it's bandwidth X at or below priority Y. There are 8 priority levels available. We'll get there. So, quick rehash on SPF calculations. Starting off, we'll create a path list and a tent list. These are key variables in the SPF calc. Step 1, we're going to go ahead and put ourselves on the path list with a distance of 0 and a next hop of ourselves, and we're going to ignore our bandwidth. And for the node that we just placed on the path list, we'll call that temporarily the path node. Step 3 says put all of the path node's neighbors on the tentative list unless a neighbor is already on the tent list or the path list with a lower cost. At step 4, if the tent list is empty, we stop. At step 5, we find the neighbor in the tent list with the lowest cost, and we move that over to the path list, and we jump back to step 2. So essentially a 6-step process covering how the router actually does the OSPF or ISIS scenario. And we're going to jump down. Hopefully you've picked up a worksheet. Those of you who may have done a lot of OSPF or ISIS internals, feel free to tune out. But we're going to run through an example exercise real quick covering SPF using the worksheet and the easel pad. And we're looking for the side of the worksheet that does not have bandwidth numbers in the diagram at the top. And we're going to calculate the best cost path from router A to router D. So step 1, we put ourselves on the path list, and that's going to be A with a next hop of 0 of ourselves. and we'll put all of A's neighbors on the tent list. So in this case, neighbor B has a cost of 5, and neighbor C has a cost of 10. We'll go through and we'll pick the item on the tent list that's got the lowest cost, which will be B. B punts over to the path list with a cost of 5 and a next hop of B. And now that we've put B on the path list, we're going to go ahead and take B's neighbors and place them onto the tent list unless they're already on the tent list with a lower cost. So B's neighbors include A, who's already on the path list. C, at a cost of 5 plus 3 is 8. So we're going to scratch out the existing C and put a new C of 8. And we're going to put a new neighbor on the tent list of D, which is going to be at a cost of 5 plus 8, or 13. And we'll select the lowest cost entity on the tent list and move that over to the path list. So now C moves on to the path list with a cost of 8 and a next hop of C. Actually, I'm incorrect. That should be a next hop of B. So we're slowly building up our routing table. And now we take the new node on the path list, and that's our path node. Take a look at its neighbors. C has a neighbor of A, but that's already on the path list. C has a neighbor of B, but that's already on the path list. C is a neighbor of D at a cost of 5 plus 3 plus 4, which is 12, which is actually lower than the existing entry on the tent list. D comes over to the path list at a cost of 12 with a next hop of B. So we've basically managed to build up our routing table so that router A can find router D using 3 hops at a cost of 12, which you'd see in your routing table under OSPF or ISIS metrics. Any questions on this first SPF exercise? Zoom through it, but we'll talk about some references on where to get a little bit more exposure to that. What we're going to do is now repeat the exercise, except factor in SPF constraints. And we're looking for a path from router A to router D that gives us a bandwidth availability of 60 megabytes or megabits per second. So same basic scenario, going from A to D. We'll start off by putting router A on the path list. Next hop is self, cost of 0. All the router A's neighbors on the tent list. B, cost of 5. Next hop B, available bandwidth 100 meg. C, cost of 10. Next hop of C, available bandwidth 100 meg. So we take the item on the tent list with the lowest cost. B moves over to the path list. Cost of 5, next hop B. We now take B's neighbors, place them on the tent list, unless they're already on the path or tent list right now with a lower cost. A is already on. We can get to C at a cost of 8, as we saw in the previous example, except there's only 50 megs available, and we're trying to build a 60 meg path. So we don't actually put the ABC entry on the tent list. We leave the existing C entry on there. And we also have a neighbor in D at a cost of 13 that does have at least 60 megs available. And that's through a next hop of B, and that's got 80 megs available. So our lowest cost path on the list is C. C moves over, cost of 10, next hop of C, and it's got 100 megs. So we take all of C's neighbors, place them on the tent list unless they're already on the list somewhere right now. A's on, B's on. Our only option is D at a cost of 14. That's a higher cost than what's already there, so the list doesn't update. We take our lowest remaining cost item on the list and punt it over to the path list. So now D is available at a cost of 13 by going through B. So it's a different path through our network because it was the only path, or at least in this case the best path, that had at least 60 megs, let's say 65 megs available to sustain what we wanted to do. The BC link with a limit of 50 tied our hands and meant that we had to go through ABD. Any questions on the constrained SPF exercise? All righty. I know it's a little different to actually go to Nanog and pull out a pen, but this was pretty valuable to understanding how a lot of this worked for me, and thought it'd be worthwhile to take a few minutes to put it in there. So we've run through our CSPF exercise. A couple of key notes on constrained SPF. Within an individual tunnel, no interface load sharing happens. The TE tunnel has single interface exit points, hop by hop. As soon as a path is found that meets the criteria, that path is selected and signaled as the LSP. Some key tiebreakers are the lowest IGP cost. We already came to that. The largest minimum available bandwidth wins in the CSPF path selection. Lowest hop count also factors in if you haven't already selected a best route. And the top node on the path list, and this ends up being somewhat deterministic based on how the router actually performs its calculation. A lot of internals that I'm not familiar with and isn't really adjustable by way of a knob in the configuration. But that ends up indicating that there are some certain scenarios where you may not fully understand why traffic's covering the path it is, and you may need to do a little bit of IGP metric redesign. I had to do this in my network. Ended up following a lot of the model of VJ Gill when they converted ATDN from OSPF to ISIS, and that really helped make my TE tunnels follow what I anticipated to be the most logical path. So, another checkpoint for where we're at. We've covered TE and config basics, TE and bandwidth concepts, calculating the path through our network. And now it's time to actually configure how to select the path through our network. As we touched on earlier, paths can be created dynamically by allowing our TE-enabled IGP to perform these calculations for us. And indicated before, it's path option, pick a number, lowest number wins as dynamic. You also have the option of creating explicit hop-by-hop paths. Define an IP explicit path by a name, and I think you can also do by number. And then within that explicit path, specify next hop addresses in sequence. You may need to experiment with this on various code releases. You may have to specify interface addresses and loopback zeros. It all depends on the specific implementation. I've run into a couple of gotchas where the tunnel path option wouldn't come up until a couple of extra data points were added to the path option. And then within the tunnel, the TE tunnel interface, define tunnel MPLS traffic path option X, explicit name, and then specify the name of the path option you've written. So you can actually write these to take specific hops if you've got parallel links between two routers, or typically you can get away with just specifying loopbacks. Again, play with your code as needed. So that's explicit hop-by-hop selection. We also have the option of doing take any path you can find through the network, but don't go through this. And that this can be a loopback, or this can be an interface address. So if you've got a link you just don't want one tunnel to take, you can do an explicit path that excludes an address. It could be a high latency link, it could be just a low bandwidth link, a low reliability link. Your network is your network, but this is particularly important if we take traffic engineering and extend it to the next level for fast reroute. You may want to have a fast reroute capability to specifically ignore the link you're protecting and use the explicit path ignore or exclusion option to exclude that. Might need to turn the power switch on the mic. Rotate from right to left.
Ken Emery from. I'm wondering, when you do the exclude, if all the other paths go away, does that still exclude that path that you manually excluded?
Repeat the question.
You've got multiple paths, and so you're excluding this one. What about if the other paths go away? Will it use the one you've excluded?
The tunnel may have let's say there's 3 path options configured. Path option number 1, you've specified next hops. Path option number 2, you've specified an exclusion. Let's say path option 3 is dynamic. Every time the tunnel reoptimizes, which we'll cover, it will try the lowest numeric path option first. So in this case, it would do a next hop calculation. If that path had insufficient bandwidth to sustain this tunnel's configuration, it would then attempt path option number 2, which would be an exclusion, say, go there, but don't go through this node or this link. And if that failed because there was insufficient bandwidth, it would then fail to the third option, which is dynamic, and would go through it. Does that help?
Yep.
Good. The key, though, is on a particular explicit path, cannot mix and match next address and exclude address. Just a limitation in the code. The calculations would probably get pretty brutal going through that. So, and this leads right to where we're going, a TE tunnel can have multiple path options. Lowest cost, based on the number before the name or dynamic, is attempted first. They're then attempted sequentially until a path can be successfully established. Depending on your architecture, it's usually best to have a dynamic option as your highest numeric option so that you can find a path through the network of bandwidth X, wherever it may be. Otherwise, you may end up having TE tunnels going line protocol down, falling out of your ribs and fibs, and reverting back to IGP forwarding. And particularly in my case, doing automatic bandwidth adjustment. If some of your traffic is traveling solely by IGP forwarding and not by TE tunnel forwarding, you have traffic that's not being counted as far as a bandwidth value over that physical interface. And if you've told an OC3 that there's 120 megabits available, when in fact you've got 60 megabits of non-TE traffic flowing over it, you potentially have a scenario where you're going to reserve more traffic than you truly have available to TE. So upon setup of a tunnel or reoptimization of a tunnel, CSPF checks the tunnel's path options in sequence. Static path options are checked hop by hop for available bandwidth. Dynamic path options do a complete search of the network for an available hop by hop path. And if there are no available paths that have sufficient bandwidth, the tunnel goes down. So we've covered everything you see. It's time to start distributing the traffic engineering information around the network. It all gets shared inside of your various IGP LSAs. There's available bandwidth per interface. That bandwidth can then be broken down into 8 priority levels, not in any related to IP precedence. It's simply numeric values. But your traffic engineering tunnels can be told to be a priority value from 0 to 7. So the high priority tunnels can push low priority tunnels out of the way if for some reason they need to resize or they otherwise re-optimize. The low priority tunnels will fall potentially to an indirect path so that your high priority tunnels take the best path that they can possibly find. Still might not be your IGP best path if you've got enough tunnel overload relative to your best path interface. But you've got some ability to tweak and tune your tunnels, implementation specific, to make this work. As a caveat, there are some dynamics as far as the tunnel versus your interface sizing and the exact sequence that the individual tunnels resize, sometimes called max fill or min fill. If you find yourself looking at deploying TE on your network, give me a holler and we'll cover over some of the specifics. It's also covered a little bit in the Traffic Engineering with MPLS book from Cisco Press, which admittedly was a lot of the origin for how I picked up on this and how this presentation's somewhat structured. There's also a way to tell traffic engineering to consider a different link metric than what you've told your IGP. So essentially it's a TE-specific IGP metric. That's passed around in the TE LSAs that signal the routers to know where they're going and what paths to use. Certain parameters on how far you can really push that. And then the third key point under information distribution, which we're not going to go into actual implementation of, is tunnel affinity. You've got, I think it's 32 bits, where you can use the bit patterns as you see fit, somewhat like BGP communities. Nobody ever tells you how to use them intelligently. You kind of have to crash into a good presentation or guideline on how to use it. But you can have the various physical interfaces on your network configured with bits that perhaps indicate they travel over satellite, or they travel over microwave, or they travel over a high latency path, or for those of you who may have territorial restrictions, meaning this content can never transit another country, you can indicate in the tunnel affinity or the interface affinity bits whether that link perhaps goes into Canada. And you can have tunnels that are configured with an affinity mask that will never select a path through the network that perhaps goes through Canada. Maybe there's some sort of export restriction, and the mere fact that those bits traveling over this particular tunnel don't belong outside US or any other boundary you may want to define. Some rather unique esoteric ways of adjusting TE. So this information is passed around amongst the various TE-capable routers in your network immediately when there are significant changes. If a tunnel is dramatically resized, the router will pass the information around to the rest of the nodes in the network right away. If there's a very small change in bandwidth reservation or something along those lines, it'll catch up to it perhaps 3 minutes later. But if it hasn't gotten around to sending that small bandwidth change LSA to the other nodes, and another tunnel happens to resize and tries to use a link where there actually isn't enough bandwidth for it to actually get its reservation, that'll cause an error, and the information which had been held for a periodic update will then be signaled immediately so that the rest of the network realizes, oops, that wasn't the most up-to-date information, and it was better to know about this change right away. There are a variety of bandwidth thresholds that thankfully are configured as percentages, so that whether you're doing this on T1s or OC768s, there are various key points that Cisco and I'm sure Juniper have defined where the information is passed. There are, I believe, 14 by default, but it's very customizable should you happen to have different traffic changes in your network. So, as mentioned before, the insignificant changes are flooded every 3 minutes by default, and if the path setup fails, it's flooded right away. So what if a new path, whether it's dynamic or static, appears in your network that's better than the current one? TE will re-optimize, and it'll do this every hour as a timer that starts the time that the tunnel comes up, not all the tunnels on one particular router. That way there's some scatter in it. But if you happen to feel that your tunnels could be signaled across your network in a better format, you can manually hop onto routers and MPLS traffic re-optimize. You can do it globally, or you can indicate individual tunnels that need to be re-optimized. And if you want tunnels to re-optimize in the event a link comes up, you can have that built in, but just in case you've got heavily flapping links, Cisco defaults that to off. When links go down, obviously there's no way for a tunnel to continue flowing over that link, so re-optimization happens right away. But when the link comes back up, by default, the traffic tunnel stays off that link. Production, real-world experience means that if you have a flapping link, TE tunnels will tend to stay off of that link for a period, in this case, somewhere up to an hour. So you essentially have flap dampening in that packets are not forwarded back onto that link for some period of time. So in the event of an actual link bounce, traffic will stay off that link. So if it ends up recurring within a short period, you've got less chance of packet loss until the rib and fib reconverge. So we've done a lot of talking, 45 minutes or so, about various concepts of TE, how to configure our paths through the network, how to get the information around the network, but we haven't put any traffic on these tunnels yet. So that's what's up next. 3 basic methods: static routes, hopefully you all understand that. Policy-based routing, obviously not a very scalable solution, but if you have particular traffic that you want to be traffic engineered, whether it's something you simply don't want on your best route, or otherwise you want it to be tracked. Maybe you want to know exactly how much traffic is going from this customer out a certain router. You can policy route it onto the tunnel so that your native rib and fib don't actually change to reflect the tunnel's presence, but particular traffic is sent over there. This is a way to do it. And the third option is AutoRoute. Basically, treat this tunnel as though it's a logical, directly connected link all the way to the tunnel tail. So send any packets down the tunnel that would be destined for either the tunnel tail or beyond. And it updates the local router's rib and fib with tunnel X in place of the IGP next hop, so that traffic going down the tunnel is now forwarded all the way to the tunnel tail, not just to one hop further based on the TE tunnel. And it preserves the calculated IGP cost all the way to the TE tail. This becomes very scalable. Essentially one line of configuration per tunnel, and poof, TE tunnels take over. The key, though, is it updates the local router's rib and fib. It does not signal the TE tunnel into your IGP. So prior routers are not made aware of this tunnel being a logical link that jumps all the way to the tunnel tail. There are ways to do that with ISIS. I believe there are ways to do it with very recent 12OS code in OSPF, but that becomes a little tricky because you end up chasing down IGP scaling problems. If you've got, let's say, 3 tunnels per physical link for load sharing capability, so that if you oversubscribe a link by 50%, 1/3 of your traffic punts over to an alternate path, you're now signaling, you essentially could quadruple the amount of links in your IGP. So that's very implementation specific and potentially risky. To do it, tunnel MPLS traffic AutoRoute announce. So we're starting to automatically route our traffic across the tunnel to a tail end based on bandwidth as talked about before. The key, though, is if you have parallel physical interfaces, traffic won't load share over those parallel interfaces unless you have parallel tunnels. And if you have bandwidth configured on those tunnels, the tunnels will, by default, load share inversely to the configured bandwidth. So if you're doing auto bandwidth, you can really end up with some divergent values there. Theoretically, it'll start off doing 1-for-1 load sharing, but chances are at the exact instant that auto bandwidth checks the traffic usage, you may have differences. Under the hood, it's limited to Ceph 16 buckets or something along those lines, so you'll get some sort of proportion. Maybe instead of being 8 this, one half this way and one half that way, you might have 7/16 going one way and 9/16 going another way, and you almost potentially could have these values drift apart and one tunnel end up being unused. The way around that is to tell traffic engineering to do load sharing based on a configured value. So if you did tunnel MPLS traffic load sharing 1000 and load sharing 1000 on 2 parallel tunnels, the 2 tunnels will load share proportionally, and auto bandwidth will track the bandwidth over those tunnels and signal the actual traffic inside the network. Obviously, the load sharing hash could mean that your traffic isn't exactly 1-for-1, but at least you've got consistency and less chance of a divergent bandwidth calculation. So the IGP can load share over equal cost paths. A TE tunnel cannot load share over multiple physical interfaces, but then again, you can simply build multiple tunnels from head to tail, and the traffic can load share over the tunnels. Alrighty, so we finally got around to putting traffic on the tunnels, and it's time for a little bit of diagnostics. When you're looking to see if traffic's going over a tunnel, obviously show IP route, pick an address. If it's routed over a tunnel, the next hop will be a tunnel interface as opposed to a physical. you may then want to take a look at the running configuration on that tunnel to figure out exactly where it's going, etc. You can also show IP RSVP reservations. This shows all of the individual tunnel reservations and their egress interface. And if you were on a particular router that is a TE head end, show MPLS traffic tunnel suboptimal constraint none, just happens to be the options that are necessary. This shows you which of your head end tunnels are currently rerouted onto a path that's different than your IGP best path. So you can essentially quickly assess which tunnels got punted off the best path because of current traffic loads or other configuration adjustments. On any tunnel or any router participating in traffic engineering operations, you can take a look at MPLS traffic engineering tunnels. For tunnels originating on the router, there's detailed information, the bandwidth information, and that also includes the consecutive statistics on auto bandwidth, how much has been clocked every 300 seconds since the last reoptimization. It'll show you MPLS labeling information. It'll show you the hop-by-hop path through the network. There's less detailed, or I phrase it as moderate information, for all tunnel midpoints and all tunnel tails. Not as much as you'd find on the head end, but at least enough to figure out where the tunnel comes from, where it's going, end hop, loop X0 addresses, etc. And you can also kind of filter this down and show MPLS traffic engineering tunnels that are only of a role that's perhaps head ends, or only of a role that's tail ends, or only of a role that's midpoints, or only of a role that's remote, meaning anything that's not a head end. Any tunnels that are traversing this router or ending on this router are covered by remote. And although there have been some poor bugs as far as calculating the values, show IP RSVP interfaces shows the allocated and maximum bandwidth available on an interface. Few key caveats if you're overlaying traffic engineering with other variables. If you've got MPLS VPNs, any time that a tunnel tail is not the egress PE, highly recommend that you add MPLS IP to the tunnel configuration. This adds a label onto the stack. Ordinarily, with MPLS VPNs, you've got an internal VPN label and an external LDP label to get you from here to there. By default, when you enable traffic engineering, that external LDP label gets swapped with a TE label. If we were in the scenario shown on the screen and a tunnel happened to go from PE on the left to PE that's towards the right but not on the end, the third route, or the second P that's shown there, would pop the TE label. When the packet arrives on the fourth router, it would only have a VPN label. If that particular VPN, VRF, was not live on the PE, the router will not have forwarding information to know how to get to the actual LDP next hop, and the packet fails. By enabling MPLS in the tunnel configuration, instead of swapping TE label in place of the LDP label, it adds the TE label on the outside of the stack, preserving the LDP label in the middle, so that when it gets to PE node 4, the third hop, the second P router, will pop the TE label. The fourth node, the middle PE, will still have the LDP label as well as the VPN label, and can figure out forwarding information to the last hop router. In doing so, pop the LDP label, and the packet arrives on the end PE with the VPN label still intact, so it's capable of being properly forwarded. Along with that, particularly if you have unidirectional tunnels that are not matched by a corresponding reverse direction tunnel, and or during the window of which you're enabling this, highly recommend MPLS LDP discovery directed hello accept, so that when you enable MPLS IP on the left end PE router, The PE router in the middle here will accept a directed LDP session from the left end PE router. Otherwise, the LDP labels will not be exchanged, and all your wonderful MPLS IP configuration on the tunnels doesn't work yet. If you're doing multicast of one form or another on your network, the multicast RPF configurations are normally based on your unicast rib. Unidirectional TE tunnels, because they don't go back and forth, cause RPF failures. Things go boom. So within your IGP on any potential router within the mesh, MPLS traffic engineering multicast intact belongs in your IGP config, so that the RPF checks are based on the rib prior to the TE overlay to update your next hops to go over tunnels as opposed to physical interfaces. Been there, done there, earned the t-shirt after a lot of mad configuration changes. So that's a real important gotcha if you've got multi-service going on inside your network. Alrighty. Any questions? The presentation's on the website. The email address is there. Feel free to ping me if you've got questions. And I'm going to go ahead and swap laptops, and we're going to go ahead and see if there's any TE going on in my network. It's usually pretty obvious from our MPLS graphs, or our MRTG graphs. Yeah, it's going to be going on. Like me? Yes, you do. Okay. This is a snippet of graphs I've pulled together. We've got relatively small network. We do about 150 to 200 megabits per second aggregate transit traffic to the internet. 4 POPs. 2 largest POPs are in Dallas and Houston. I've got an overload of egress traffic coming in from a Houston customer. We're punting it out. Our various 3 transits in Dallas, and we've got 4 parallel DS3s, 2 between Core 1 and Core 1, and 2 between Core 2 and Core 2. Top graph here on the left indicates the aggregate traffic over those 4. Due to some asymmetrics in our redundancy configurations, we've got an OC3 link that's not backed up by a parallel OC3 link. We tend to have a lot more traffic on the links between Core 1 and Core 1 than we do on the links between Core 2 and Core 2. Here's traffic on one of the 2 between Core 1 and Core 1. Green inbound is coming from Houston into Dallas, and the various white dips happen to be instances when traffic got up over our 30 megabit IP RSVP bandwidth threshold, and then within a span of 15 minutes, in some cases a span of 5 minutes, TE kicks in and punts 1/3 of the traffic over that physical interface onto some other path, which typically is one of the DS3s going from Core 2 to Core 2. So it particularly happened here about 9 a.m. Central, again, or just before 11 a.m. Central, and we're tickling the threshold right now, or very close to now, on that one. Likewise, on the second DS3 from Core 1 to Core 1, we've touched it. And some of these white dips indicate that it could have rerouted. A lot of the big spikes showing up here, Core 2 to Core 2, as well as here, Core 2 to Core 2, signify traffic engineering had kicked in. And particularly here in Houston, the inter-core link, or it's actually a bundle of 2 POS links, tends not to have any traffic whatsoever unless TE is kicked in. So here, about 11 a.m. this morning, we were traffic engineering about 30 megabits over an alternate path that added 2 hops. They're not really experiencing congestion except for brief periods, perhaps, that you can't see in the 5-minute window. But this is, obviously I need to upgrade these links. I'd like to flip 3 of them into an OC3, but haven't gotten there yet. This is somewhat status quo. It's a great way to see the traffic engineering works for us. Like I said, this is aggressive 15-minute bandwidth. with a network as small as what I'm running, surprises do and can and do show up at the spur of the moment. So this keeps us a little bit safer, so that while I'm here and not getting called, my junior staff is able to weather the surprises a little bit better. Any questions? I'll be available for a while if you've got anything you want to see specifically. Thanks for coming.